Hi, so this is a video that I put out as a short, and what it is it's a cloud of particles that are going through a Duffing oscillator simulation. This is a cubic nonlinearity on a single degree of freedom system. This level of nonlinearity, it's acting pretty chaotic. Now, this is a standard single degree of freedom linear system with no forcing, and you can see if, in this case, I gave it initial velocity, no initial displacement, and I'm overlaying some plots that I generated in Python with what I generated with my Blender nodes. Now, there's three things being plotted here. There's Euler's method, improved Euler's method, and then a Runge-Kutta. And Runge-Kutta is the cone, the sphere is the improved Euler's, and the Euler's is the square. And you can see the Euler's method isn't as close to the exact solution as the others, but in this situation I'm actually running a system with some forcing, and you can see that if I lower the time increment enough, it starts getting closer to the exact solution. But I have to really lower it down quite a bit in order for it to do that, and even then it starts deviating from the exact solution pretty soon, especially for a system with forcing. And the single degree of freedom system, you can go to a previous video and see that I made, and kind of see the derivation and how that's all set up. It's pretty easy to change it to add forcing, and it's pretty easy to add this nonlinearity in there and get this kind of crazy looking behavior. This is kind of similar to what you'd see like pictures on the internet of a Poincaré plot. This is a kind of a phase space plot, and all these I'm kind of comparing them to exact solutions, single degree of freedom, and with and without forcing. I'm using Craig's book, and that's Introduction to Structural Dynamics, and then the chaotic Duffing oscillator I'm using from equilibrium to chaos, and that's by a guy named Seidel. The methods that I'm showing here for the time integration is Euler's method, which is if you have a system that's x dot equals fx, and fx can kind of be anything. It could be a single degree of freedom system like I have here. It could be a model for an aircraft. It could be anything. X of t plus delta t, that's the time increment. So it sort of marches through a system where you start at x of t, which is here, it's I'll show you later, it's a state space kind of representation of the system, that the next increment, which is at x t plus delta t, is equal to xt plus f of x at t times delta t. So you can kind of march through the solution like that. Improved Euler's kind of does an averaging of f of x at n, and here I'm kind of changing the notation because n is sort of a variable and it goes from 1 to however many increments in time you want to calculate it for, and then there's an n plus 1, which is the next increment. So the improved Euler's kind of does an intermediate calculation here where it comes up with an estimate similar to the Euler's method, and then uses that in the next iteration of the solution. So it's kind of taking an average of the function at x of n, the function at this x tilde n plus 1, and it does a little better job there. The Runge-Kutta is a little more complicated, and here I'm showing all the equations there, and it's just kind of coming up with different slopes for the solution, and you can look this all up on Wikipedia or whatever. and comes up with an estimate of the x of n plus 1, and this is the Runge-Kutta 4-5, I believe. And so if we go into the nodes, you can see that the node that I created, that's the most essential, kind of evaluates the f of x delta t. And here I'm showing the single degree of freedom system, how you would write that in the form below. So this is mx double dot c x dot kx, where double dot is acceleration and the dot is velocity, and how you can write that into a state space equation that you can throw into this. And so here I'm in this kind of central node to the whole system. You can see the inputs are time, the increment of time, velocity, displacement, stiffness, mass, damping, and the forcing. And here I'm not really doing anything with the forcing, you can see, and that's because I'm just looking at the system right now with no forcing. I could add forcing, and as I wrote out the equations of motion, you can see where that would go into the equation. As I get out here to the adds, I would just add the force input here. And then if I wanted to do something like the Duffing oscillator, I would take this x and then I would cube it, and that would get added to these equations. So you would just have a cube term of x in that second row of the equations of motion that I was writing. So the outputs that I want are the t of n plus 1 at n plus 1, x at n plus 1, the velocity at n plus 1, and then fx and f dx dt, both multiplied by the time increment. So the nodes aren't that complicated. If you compare this to the equations that I showed you earlier, you can see that here, this is the, if I first follow the first row of the equation, I have x kind of following over here, and I have dx dt here, and so that dx dt is being multiplied by dt, and that is added to the old x, and then that becomes x of n plus f x of n dt, and so that's the output x at n plus 1. And then what I wanted to do is just take out that f xn times dt and make that an output. You can see later that kind of simplifies some of the node setup. It can do everything with this one node rather than make a bunch of different things. It kind of simplified things. So the second row of the equation is I have x times k, I divide by m, and then down here I have the velocity times damping, and that's divided by m. Those two are added. They're both negative in the equation, so both are multiplied by -1, and then I multiply that by the time increment. And so you can see this is, again, f of x times dt, but this is the velocity term. And so if I add the original velocity to this newly calculated velocity, the f of x dt, you can see that's the velocity increment of this time increment. That goes in to make this dx dt at n plus 1. And then if I go back to this node and just feed that in, I'm just getting that f of the velocity term times dt. So that's the state space equation. And if I go out of that, here I'm in the Runge-Kutta method, but if I go into the Euler, you can see it's pretty simple.
The inputs are here, time, delta time, and these are just the initial velocity and displacement, and then these are the K, C, M, and F values that I'm using. I don't have forcing in there yet. So you can see these just are fed into that node group, and this is the same node setup that I was just showing you. And then these outputs are going straight into the outputs except for this X, the dx dt, and the time. And so this time is just the time increment, so that's the output at t n plus 1, and then x n plus 1 and dx dt n plus 1, those are the outputs. And so in this simulation zone, it's just incrementing through this. So here I'm taking this displacement at n plus 1 and dividing by some value, and this is all hopefully to try and get something that I could overlay on top of this plot that I generated in Python. Of course, what I'm doing in Blender is on the same scale as this image that I output, showing the difference between the exact solution Euler's method and the proved Euler's method. And so the X here is the Z displacement, and that goes into a set position. And then the Y, I'm using time for that, and the X is 0. And so those are setting the position of the geometry that's being read in, which is just a point, and just one point there. And so that's all calculated at each increment. And then I'm doing an instance on points, and I have a cube that goes into there. I gave it a material, and that gets fed into a join geometry. I had 3 setups, and then that goes into the output. So that's basically the Euler's method. The improved Euler's method is similar, and I showed you the equations for it, and you can see that the x of n plus 1, this would actually be that x n plus 1 and dx dt n plus 1 tilde, and then those go into the next step, which is exactly the same node setup, and then those two are added. The 2 velocities are added, the 2 displacement increments are added, and then they're divided by 2 to get that average. And then you can see here I'm following x and dx dt, and then these are being added to what's being calculated from this node group, and then those are both going into the outputs here, along with the time increment that's coming from that first node, this t of n plus 1. So that's all pretty simple, and you can see here I'm doing the same thing. I'm taking the output displacement, feeding that into Z. Y, again, is the time, and then that's going into a set position. And here, instead of a cube, I'm using an icosphere, and that's the same thing. It's going into that join geometry. And then down here, you can see I'm using a cone for this Runge-Kutta method, and this is a little more complicated, but if you go back to the equations that I've shown you before, you can see that I'm taking the f of x dt terms. It's k1, k2, k3. These are all the same nodes internally as the other ones that I showed you before. I just gave them different names here. And so you can see that x and dx are added here, and then that goes into the next increment for k2, and then those go into the next increment for k3, and then those go into k4. And you can see these are all just multiplications and divides and adds, and it's just writing out those equations for the Runge-Kutta method. And then here I'm adding to the original velocity and displacement. Those are becoming the outputs. And then here the same thing. I'm taking the displacement output, x of n plus 1 actually, and that's going into this divide, and that's going to z, and that's going into a set position. So I won't go through all the nodes set up, but if I kind of zoom in here and pause for a little bit, you can kind of see what I've done. And I kind of broke out these nodes so I could put a label there to kind of show you what's going into each one, so hopefully you can follow. So it's a little more complicated, but you know you get it right when it matches the other methods. And start off with a simple ring down of a system with an initial velocity only, and you can once you get that, boy, you know you got it kind of working, and then you can go ahead and add forcing or add a cubic nonlinearity or whatever you want. For whatever system you have. So that's basically it. I wanted to show you the three methods and how to do it. And if you have any questions, you want maybe some snapshots of the node setup to show you things a little bit better, just let me know and I'll try to help you out. Okay, thanks a lot. Bye. So I have my setup here where I was looking at a system with forcing. You can see there's the plot there. And I wanted to show you how I modified this node group here. You can see it's all very similar, except for here I have the force output that's coming down here, multiply it by 10, and then up here, this multiply, this is the time going in there. You can see time, follow it down. So that time is being multiplied by this 10, and what this is doing is calculating a like an omega t that goes into a cosine function and then is multiplied by an amplitude. So I'm just putting in a cosine sinusoidal forcing function, and then you can see that this is added to the other mess of nodes that I have describing that single degree of freedom system without forcing, and it's added there, and then that goes into the multiply here, where that's multiplied by this delta t there. So it's just a simple addition of whatever forcing you want, and here I have a cosine function, but you can make it anything you want, and so that's this one. So okay, so now we're in the Duffing oscillator, and let me zoom in here, go into that node, and you can see a lot of it's the same. Here's the forcing function that I showed you before. Of course, some of the parameters are changed to match the example that I got from the Seidel book. Here's 1.8 is what the cosine function is. That's the frequency of that function. And then here, x is going down into this multiply, and I was playing around with factors on x before. I take it to the power of 3 here, and then after, and I decided, I'll just show you the example where these are all 1. And this is divided by m, and then that's added to C damping times velocity divided by mass, and then displacement times stiffness divided by m, and that's all added together, and then multiplied by -1, and then that's added to this forcing function, and that gets you that f of x for the f of x dot, actually, for the Runge-Kutta method or Euler method or the improved Euler method. This whole thing is just calculating that f of x. So that's a simple addition, and if I zoom out, I'll show you the other inputs that I used. And here, in Seidel's book, he has these parameters set up. Here I'm using a delta t of 0.03. That wasn't in his book, actually. But the k minus 2 here, 0.4 for C, m of 1, and then the forcing here is 2. Actually, if I change that to 5, we can get a little more chaotic type motion. So what I did here, I have a curved line, and then I'm using count to adjust how many are created. So if I change this to 2,000 and then restart it, boy, I get a lot more points. And it actually calculates everything fairly quickly. And the more points I throw in there, what I'm doing for each one, I'm taking the position and separating it, and then using that as my dx dt and x. What I did, I set up the initial displacements of the initial positions of all these nodes on that curved line to be different in space, and then used the z and y coordinates of those nodes as if they were the initial position and velocity of those points. So I had a whole set of nodes with different initial conditions, and so you can get kind of this cloud effect, because a chaotic system will behave differently depending on your forcing input and then also your initial conditions. So that's all there is. So go ahead and play around with it on your own, and if you have any trouble, just go ahead and send me a message, and I'll try to sort out what's going on, or provide you with more information so that you can set something up like this. Okay, that's it. If you like this, go ahead, click like, subscribe, and I'll see you in the next one. Thanks.